I want to talk a little bit more generally about limits, the different types of limits we're going to run into. There are a few varieties of limits. We haven't hit them all yet, but we've hit most of them already, mostly looking at those graphs. So these are the 5 types of limits that we're going to run into in this class. The first one is the plug-it-in variety. It's called direct substitution. So this is the type of limit we're going to see for a continuous function. So if a function is continuous, then we can just plug in the value that x is approaching, and it doesn't have to be x. It could be any variable approaching something. We can plug it into the function and get the limit. Okay, this works when it's a continuous function. When it's not continuous, we're going to have all these other types of limits. So we're going to have limits with removable discontinuities. We're going to have limits with non-removable discontinuities. And the unbounded limits are going to they're going to fit into that non-removable discontinuity class. And we'll look at pictures of all these later. We're also going to deal with limits at infinity. So all the limits we've done so far, we're looking at what happens when x approaches some constant value. When x approaches 0, when x approaches 7, when x approaches pi even, we could do. These limits at infinity are going to be what happens as x increases without bound, as x goes to infinity. So if x gets really, really big, what's going to happen with the function? Or if x gets really, really small, approaching negative infinity, what's going to happen? And these limits are actually going to correspond to what we know as horizontal asymptotes. So what happens with the function as you approach infinity is going to correspond to that idea of horizontal asymptotes. So let's look at a few different kinds here. The function y equals x squared, we know what that looks like, right? So we could draw a picture of that on a graph. It's going to look something like that. And as x approaches 4, well, what do we know about this function that's going to be useful here? What property does that function have that allows us to evaluate this limit very easily? It's continuous. All right, so the continuity of this function allows us to use direct substitution. It just says that the limit of this, the limit as x approaches 4 of x squared, is just going to be 4 squared, which is 16. So if we look at the graph helps us in the sense that the graph is continuous. And we know that the graph of this is continuous. All right. More interesting, this is an example we looked at yesterday. This is a removable discontinuity. This function is a line with a hole in it. So this function looks like this. And the hole just happens to be where we want to evaluate our limit. It's convenient, right? So even though it has this discontinuity at that point where we want to evaluate the limit, we can't evaluate it because... But we can't evaluate it because... Yeah. Both sides approach the same value. It's removable would be another way to say it. So if we were going to evaluate this analytically, we could factor the numerator, x plus 1, x minus 1, and we are allowed to cancel here. We're allowed to reduce this because we know that x is never going to equal 1, at least as far as evaluating this limit. So this is equal to the limit as x approaches 1 of x plus 1. Don't forget your parentheses there. So this would be the analytic way of evaluating this limit. And now this turns into a direct substitution one. And when we have a limit that is indeterminate to start with, if we plugged 1 in here, we would have 0 divided by 0. That's indeterminate. Our goal is to manipulate it so that it's a direct substitution limit, so that it's not indeterminate. So now we can use direct substitution. Plug 1 in and we get 2. Okay, a non-removable discontinuity. I like this function. What's this function going to look like? So the absolute value function is a v, but then we're dividing that by x then. So I think the best way to think about this is, what's this going to look like when x is bigger than 0, to the right of the y-axis? Well, it's just going to be x divided by x, right? So it's going to be a horizontal line at 1. All right. Is it going to equal 1? Is it going to equal 1 at 0? No. Why not? Because it would be 0 at 0? What would it be at 0? Indeterminate, right? And actually it would just be undefined because it's not a limit at 0, it's just 0 divided by 0, and we can't divide by 0. Which is kind of confusing because in this case 0 divided by 0 is not indeterminate, it's undefined. But when we're dealing with limits, 0 divided by 0 is indeterminate. Okay, anyway, what is the limit of this function then as x approaches 0? Does not exist. What if I asked you what's the limit as x approaches 0 from the left? It would be -1. How about from the right? +1. So since the -1 and the +1 don't match up, we have a jump discontinuity in this case, then it does not exist. And the abbreviation DNE is universal. You can use that for me, you can use that for the AP test, and everybody's going to know that means does not exist. All right, then we have an unbounded limit. Unbounded limits are a little bit tricky, and well, this one's not tricky. This one's pretty easy. I've got the graph here for you, so we didn't have to figure out what that looks like. But the limit as x approaches 1 of x squared plus 1 over x minus 1. This time that discontinuity is not removable. We can't cancel out that x minus 1. So what we end up with is that vertical asymptote. So the unbounded limits are going to happen when we have the vertical asymptotes. I think we can tell pretty quickly this limit is going to be does not exist. We would have to say does not exist for the two-sided limit, but each of the one-sided limits exists. The one-sided limits are going to be infinite limits or unbounded limits. So as we approach 1 from the left, what's that going to be? Negative infinity. And as we approach 1 from the right, it's going to be positive infinity. Last one here, limits at infinity. So if we want to say, okay, what's the limit as n approaches infinity of n plus 3 over 2n? Again, what I said before, that corresponds to a horizontal asymptote. We're going to deal with this later when we do the area problem. We're going to look at limits at infinity a lot more closely because those are the type of limits we're going to have to use to solve that one. But we can see here that as x approaches infinity, it's going to decrease, and it's going to keep decreasing forever as x increases without bound, but it's never going to decrease past this horizontal asymptote. So as we get further and further out, it's going to get closer and closer. And we can get as close as we want to it. We can get within 1/100th of it, or 1/1,000,000th of it, or 1 Googleth of it. We can get as close as we want by going far enough out. And again, that's the idea of the limit. We get as close as we want to it. So what is this limit going to be? 1/2. You can kind of see that from the graph. Do you guys remember the trick for evaluating that for the horizontal asymptote? The degree of n is the same on the top and the bottom, so divide the leading coefficients. So it would be 1 over 2. If the degree on top is smaller than the degree on the bottom, then it's going to be 0. If the degree on top is bigger than the degree on the bottom, then there's not going to be a horizontal asymptote. There might be a slant asymptote or even a curved asymptote, but we won't worry about those.